This is a short demonstration of the alpha version of SpectraSounds. The concept behind this tool is to take optical frequencies and translate them to audible frequencies. First, quickly looking at the user interface, we see the periodic table along with some graphs. For example, here we see the optical spectrum of neon. Atomic spectra represent the possible wavelengths of light, which can be emitted when an electron in an atom changes energy levels. Using the simple Bohr model, as shown in this cartoon from the ChemWiki page at UC Davis, we get the basic idea. An electron, for example, goes from the third energy level to the first and emits light of a certain frequency. These energy levels are unique to each element, meaning no two spectrum is alike. Again, looking at the UC Davis page, this is seen in the predicted series of the hydrogen atom. And put another way, each element plays its own distinctive chord. The problem is that optical frequencies are in the gigahertz to terahertz range. That's a trillion hertz, far, far beyond the threshold of our hearing, which is about 20,000 hertz. So the question is, how exactly do we map optical frequencies of elemental spectra to audible frequencies? A simple linear mapping wouldn't work due to the relative separation of the lines in the optical spectrum. For example, the frequency difference between a line at 600 nanometers and one at 601 nanometers, only 1 nanometer away, is approximately 832 gigahertz, vastly larger than the range of audible frequencies, which is roughly 20 hertz to 20 kilohertz. As an alternative, we used values collected from the NIST Handbook of Basic Atomic Spectroscopic Data and found that the optical frequencies for elements in the periodic table span the range from 24 gigahertz, here shown 24 times 10 to the 9, to 17,485 gigahertz. 24 gigahertz is one of the transitions of hydrogen, and 17,485 gigahertz is one of the transitions of lithium. So, simply by dropping the giga prefix or removing the exponential part, we find that the significans 24 to 17,485 fit nicely into the range of audible frequencies. So, using this mapping, let's hear what hydrogen sounds like. The elements are fairly atonal, with a few exceptions like magnesium. There's magnesium. We can see a nice beat frequency associated with the two lines being very close to each other. One thing that's really neat is you can actually hear the shell structure of the atoms as you traverse across the table. For example, listen to the lanthanoids. We can also move down a column. For example, let's hear what the chalcogenides sound like. Some features are the ability to manipulate the tone duration and wave envelope. For example, we can make a very short tone or a very long tone. And in hydrogen, you can see the wave envelope very nicely. What we've done is use a linear increase and decrease of the wave set here by the percent attack. So if I want a very sharp attack, I can put a very short percentage. If I wanted a very long attack, I can change that to 25, allowing me to change the feel of the note. Another thing that we can do is we can reduce the total number of lines that are being used to create the tone. For example, in neon, what we can do is we can change the threshold to be, for example, 70% of the maximum. It'll recalculate the table, and again, we can now see neon, and only the most intense lines remain. This allows us to have a fairly cleaner sound associated with the tones. Another feature is the ability to play compounds by entering the chemical formula in this text box. What the program does at this point is to take each part of the formula and make it the same total length. So for example, water, H2O, would play two hydrogens each half-time of the lone oxygen. One feature we are currently working on is to add additional tracks. So you could imagine playing an underlying track of water over and over with various elements floating along on top of that track. Just to give you an idea, a few of the other compounds that I've picked out were one, caffeine, for example. You can just cut and paste. Change the tone duration if we want. Another one that I like is working with 3,5 semiconductors. This would be a structure, heterostructure. We could also play salt and water. And one that I found to be very interesting is if I just simply play fluorine, oxygen, nitrogen, carbon. Oops. These are just a few of the options in the first version. Our plan is to port this idea to a more universal programming language and release it as an open source project. So check in for updates, and thank you for checking it out.